When we hear the word mirror in everyday life, we often think about the aluminum mirror that we have at home. Many people do not realize that it's possible to make a mirror without the use of a metal. For example, a mirror entirely made of glass. But how does such a mirror work? As you probably know, when a light beam reaches an interface between two materials, a portion of this beam is reflected. A multi-layer mirror is basically made of multiple layers of different materials. At each interface, a portion of the light will be reflected back. So if you add up all these reflections, you can reflect more than 99.9% of your initial beam. My work focuses on the deposition of such layers, that we also call optical thin films. An important factor is the thickness of the film. Because of the wave nature of light, the reflections at each interface might cancel each other instead of adding up. By choosing an adequate combination of thicknesses, we can produce high reflection coatings, anti-reflection coatings, and much more complicated structures. What sort of thickness do we need for these coatings? Well, let's take the thickness of a human hair as a reference. The thin films that we deposit are between 100 and 1000 times thinner than a human hair. And for our application, we need a very good control over this thickness. Now, you might wonder, what is the novelty about my research? After all, these coating technologies are already well developed. For instance, if you're wearing glasses, they probably have an anti-reflection coating and an additional coating to reflect part of the blue light. Well, in the field of photonics, we are developing lasers that are more and more powerful. And it becomes harder and harder to make optics that are able to withstand such high powers. In particular, optical coatings are often getting damaged first. The specificity of my research is that I am investigating coatings based on crystalline materials. Compared to typical glass, crystalline materials offer better thermal and mechanical properties, which makes them a candidate of choice for the next generation of optical coatings for high-power lasers. To deposit these crystalline films, I use a coating method called Pulsed Laser Deposition. A ceramic target made of the material to be deposited is ablated by a UV laser in a chamber with very low oxygen pressure, around 50,000 times less than atmospheric pressure. This produces a high-velocity plasma, which deposits on the sample. The growth of a crystal requires much more energy than amorphous material, which is why our sample needs to be heated by a laser to a temperature often exceeding 1000 degrees Celsius. To conclude, my goal is essentially to optimize this deposition process, and I hope to produce crystalline films with sufficient quality to be used as optical coatings. Thank you for your attention.